Okay guys, this is where we were when my battery went dead a little earlier. So battery's charged, we're back up and running. So we're talking reaction calorimetry. Okay, in reaction calorimetry, we're working under conditions of constant pressure, usually in an open beaker, and any energy lost or gained by the reaction is either released into water or absorbed from water. So Q of the reaction is equal to the negative Q of water equals the negative of the mass of water times the heat capacity of water times the change in temperature of the water. So we're going to look at problem 9.8 on page 387 in the textbook, and we're going to look at a reaction calorimetry problem. So 9.8, 384, 387. Let me find the page. Okay. So let's look at it. All right. It says the addition of hydrochloric acid to a silver nitrate solution. According to the following reaction, silver nitrate plus lead HCl goes to silver chloride and nitric acid. You combine 50 milliliters of the 0.1 molar silver nitrate with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter. The temperature changes from 23.40 degrees C to 24.21 degrees C. Okay? Calculate the delta H for the reaction. Given that we have a 1.00 gram per milliliter density of the solution and a heat capacity of the solution of 4.18 joules per gram degree C. Okay, essentially we are looking at a water solution, okay, and with this water solution we're having a reaction between the HCl and the NaOH. So I know that Q of the reaction is going to be the minus Q of the water. So I need the mass of the water, the heat capacity of water, and the change in temperature for the water. The mass of the water, if I mix 50 milliliters and 50 milliliters together, I have 100 milliliters of solution at 1 gram per milliliter. So that's 100 grams of solution. The heat capacity is 4.18 joules per gram degree C. And the temperature started at 23.40 degrees C and ended up at 24.21 degrees C. So 21.40. So our change in temperature is going to be 24.21 minus 23.40. So that's 0.81 degrees C. Not a huge change, but it's a change. So our Q for our reaction is the negative of 100 grams times 4.18 joules per gram degree C times 0.81 degrees C. So 0.81 times 4.18 times 100, I get a minus 338.58 joules. Now I should only have two significant figures, so I go 3.4 times 10 to the 2 joules, and it's negative. The negative tells us the reaction was exothermic. It released energy. Okay? Now we found the Q, but this problem wants us to go one step further. It wants us to find the delta H for the reaction. Well, this Q, okay, Q here is for 0.010, well, is for 50 milliliters, 0.010 molar HCl reacting with the same amount of silver nitrate. So what I need to do is I need to now calculate, I'm going to write this up here, our Q of reaction is minus 3.4 times 10 to the 2 joules. Okay? Now, I need to find the delta H for the reaction. Now our reaction was HCl plus AgNO3 going to AgCl plus HNO3. Notice everything's in a 1-to-1 ratio. This is the amount of energy released from the reaction of the 50 milliliters of the 0.1 molar HCl with 50 milliliters of 0.1 molar silver nitrate solution. So to find what I want, the first thing I'm going to need to do here is I'm going to need to calculate moles of HCl. So we know that molarity times volume equals moles. So the molarity was 0.10 and the volume is 0.050 liters. So I get 0.05 times 0.1. I get an answer here of 5.0 times 10 to the minus 3 moles. So since this delta H comes with 1 mole of HCl, all I have to do is take the minus 3.4 times 10 to the 2 joules and divide it by 5.0 times 10 to the minus 3 moles. So if I do that, I get 6.8 times 10 to the 4 joules per mole of HCl. Well, there's only 1 mole of HCl in that reaction, so delta H here is minus 6.8 times 10 to the 4 joules. Or you could have written it as minus 68 kilojoules. Okay? So anytime you were asked to find the delta H for reaction, we first find the Q for the amount of material that we've reacted and relate that back to how much is in the reaction in the balanced chemical equation. Okay? Now, let's talk thermochemical equation. A thermochemical equation is an equation that includes the delta H of the reaction. Okay? So if we look at the reaction, 2 water molecules gas breaking up into 2 hydrogen atoms in the gas phase plus an oxygen in the gas phase, we get a delta H of plus 572 kilojoules. It's an endothermic reaction. So what we could say here is that the decomposition of 2 moles of water requires 572 kilojoules of energy. And it produces 1 mole of oxygen and 2 moles of hydrogen. So let's say that you had 10 grams of water and I wanted to know how much energy it was going to take to decompose that. Well, using our basic stoichiometry, anytime I'm given grams of anything, then we know the first thing we want to do is go to moles. So I go 1 mole of water for every 18 grams of water. And then from that balanced chemical equation, we know for every 2 moles of water, it requires 572 kilojoules of energy. So if I do the math, 10 divided by 18 times 572 divided by 2 gives us 159 kilojoules of energy. So to decompose 10 grams of water, we'd need 159 kilojoules of energy. So let's look at problem 9.7. It's on page 385 in your textbook. So if we look at the problem, it says, What mass of butane in grams is necessary to produce 1.5 times 10 to the 3 kilojoules of heat? What mass of CO2 is produced? Well, I'm just going to worry about the first half of this. The back half is just a straight stoichiometry problem. Okay? So let's look at this. We're given 1.5 times 10 to the 3 kilojoules of energy, and we're asked grams of butane. Now, the reaction we've got is C4H10 plus 13 halves and O2 going to 4 CO2s, 5 waters, and delta H here is equal to minus 2,658 kilojoules. Okay? So I'm going to want to go from kilojoules first to moles of butane. And the moles of butane is the C4H10. And then I want to go to grams of butane, because we were asked grams of butane. Now the relationship here is for every 1 mole of butane, C4H10, we release 2,658 kilojoules of energy. Okay? To go from moles of butane to grams of butane, we're going to need the molar mass. So that's 4 times 12.011 plus 10 times 1.0079. So 1 mole of butane has a mass of 123 grams of butane. Okay, so we're going to start out with our 1.5 times 10 to the 3 kilojoules. Oh, excuse me, yeah. And that should be negative because it said it was released. Okay? Times 1 mole of butane, C4H10, for every 2,658 kilojoules released, negative sign. And then we have 58.123 grams of butane for every 1 mole of butane. Okay, so notice kilojoules and kilojoules divide out, moles and moles divide out. I'm left in units of grams. The negative and the negative here also divide out. So 1.5 EXP3 divided by 2,658 times 58.123. I should have 2 significant figures in my answer, so 33 grams. Okay, it's just your average run-of-the-mill, old, ordinary stoichiometry problem. We just use energy in it. Okay? Now, this problem is like the one that we kind of worked in the before this when I was doing Q. Let's look at this. We've got the reaction 2 sodiums plus 2 waters giving us 2 sodium hydroxides and 1 hydrogen gas, and it asks us the delta H for the reaction. And we're given that we have 2 grams of sodium with 25 grams of water, and the temperature of the water changes from 25 degrees to 27.3 degrees. Let the enthalpy change for the reaction written above. So the first things first, sodium and water are both reactants here, so I need to know which is the limiting reagent. We've got, with 2 grams of sodium, we've got 0.087 moles of sodium. 25 grams of water, I got 1.4. Since they react in a 2-to-2 ratio, it's very obvious that sodium is our limiting reagent. So to get the Q of the water is going to be the mass of the water times the heat capacity of water times the temperature change, which is 240.58 joules. That's the negative Q of the reaction. So Q of the reaction of 2 grams of sodium is minus 240.58 joules. Now let's do the stoichiometry part. We have minus 240.58 joules for 2 grams of sodium times 22.99 grams of sodium for every 1 mole of sodium. And that gives us a minus 2,765 joules per 1 mole. Now, since there are 2 moles of sodium in the balanced chemical equation, delta H for the reaction would be 2 moles of sodium times a minus 2,765 joules for every 1 mole of sodium, or minus 5,530 joules. Okay? Now, we're not going to worry about looking at problem 9.8. We've already essentially done 2 of these kind of problems. Okay? So let's talk a little bit about other ways to do things. When we look at trying to get the delta H for a reaction, we can also think about bonds made and bonds broken. So if we wanted to get the delta H of a reaction, we could sum up the energy of the bonds broken minus the sum of the energies of the bonds made. I'm not going to worry about that too much. You guys can look at problem 9.10, but don't concentrate on it, okay? All right, now we're up to Hess's law. As we've seen this semester, okay, sometimes we can think of a reaction as a sum of a lot of steps. Okay, so A plus B goes to C, C plus Q goes to X, and X decomposes into Z plus P. All right? So Hess's law says that the heat energy of a reaction of an overall process is the sum of the heat energies of the individual steps. So if it takes 3 joules to do the first step and you release 7 joules in the second step, the sum of those two would be a minus 4 joules released overall. So if we were to know the heat of reactions of a group of reaction, we could find the heat of reaction of our overall process without having to experimentally do that reaction. So to calculate the heat of the reaction for a target reaction, you need to identify the target reaction, the one you want, figure out how to add up the given reactions to get the target reaction, and that tells you what you're going to do with the addition of the delta H's. Now remember, if you reverse a reaction, you change the sign on delta H. If you doubled a reaction, you double the delta H. If you cut it in half, you cut the delta H in half. So Hess's law can be taken a step further. Wait a minute, let me see if I've got an example problem here that I would like us to work with that Hess's law approach. Come on, no, I don't want lattice energies. You know, your book doesn't have an example. Wait a minute. Now let's look at problem 9.9 on page 389. Okay? Okay, it says find delta H for the reaction, giving that reaction 2 dinitrogen monoxides plus a nitrogen dioxide going to 3 nitrogen monoxides. And we're given the reactions, 2 nitrogen monoxides plus an oxygen goes to 2 nitrogen dioxides, and then a nitrogen plus an oxygen goes to 2 nitrogen monoxides, and 2 dinitrogen monoxides goes to 2 nitrogens plus an oxygen. Boy, say that 3 times fast. All right, guys, so what we're given here is our target reaction. That's the reaction that we're trying to create. Okay, so I'm going to start writing things on the board. So N2O plus NO2 goes to 3 NOs. And I know the delta H for this reaction. Now the first reaction we're given is 2 NO2s plus, 2 NOs plus an O2 going to 2 NO2s, and the delta H here is given to us as minus 113.1 kilojoules. Now, in this reaction, nitrogen dioxide is a product, and I need it as a reactant. Of the 3 reactions we were given, that's the only one that has nitrogen dioxide in it. So one of the things I know is I'm going to have to reverse it. On top of that, there's only 1 nitrogen dioxide up here. So I've got to reverse that, and I've got to cut it in half. So if I reverse that, then I am going to have the reaction 2 NO2s going to 2 NOs plus an O2. Okay, and I want to cut it in half, so I'm going to take that down to 1, that down to 1, and that's 1/2. And the delta H is going to be 113.1, that's negative, I make it positive, I divide it by 2, I get 56.55 kilojoules. Okay, so let's make sure that we see that, okay? So, there's when we've divided it in half and we've reversed it, okay? Now, the next reaction we're given is nitrogen plus oxygen going to 2 nitrogen monoxides, and the delta H here is plus 182.6 kilojoules. Now when I look up here, I've got 3 nitrogen monoxides. This one's got 2 nitrogen monoxides. The nitrogen monoxide is on the right side, but I don't have the right number. So what I'm going to have to do is I'm going to have to take this reaction and multiply it by 3/2. So I get 3/2 an N2 plus 3/2 an O2 going to 3 NOs. So my delta H, I'm just going to have to multiply that by 3/2. So 182.6 divided by 2 times 3, I get a plus, and that's trying to die on me, so a plus 273.6 kilojoules. Okay, so let's make sure you get a good look at that. Okay, so I took that reaction, I multiplied by 3/2, and I got my new delta H. Okay, now our last reaction that we're given is the 2 nitrogen dioxides going to a nitrogen plus an oxygen, and it has a delta H of minus 163.2 kilojoules. Now, in our target reaction, we've only got 1 dinitrogen monoxide. So I'm going to have to divide everything here by 2. So if I divide it by 2, I get NO2 going to, that should be NO2, to 1/2 an N2 plus 1/2 an O2, and the delta H would be 163.2, and make that negative, divide it by 2, I get minus 81.6 kilojoules. Now, if we have everything set up correctly, when I add this together, stuff's gonna start canceling out. So let's see if it works for me. Okay? So I'm going to take brown here. So I want you to notice that I've got half a nitrogen here. So if I take half away from there, that gives me 1 nitrogen. And if I take half away here, that leaves me with 1 nitrogen. And then, let's see, I've got an N2O here. I've got an NO2 there. I've got a half an oxygen there. So 1/2, 1/2, that should have been, that takes it down to 1/2 an O2. I've got 3 NOs here and an NO there. I've got 4 NOs. Let's see, what have I screwed up? I have screwed up something, guys. Let me double check everything here because I've screwed up something. So let me rework this, because I wrote something in wrong. So let's start with our first reaction again. We've got 2 NOs plus an O2 going to 2 NO2s. And we've got an N2 plus an O2 going to 2 NOs. And then we've got a 2 N2O going to N2 plus O2, and I've got a 2 here. I think I see where I made a mistake. My delta H for the first one is minus 113.1 kilojoules. My delta H for the second one is 182.6 kilojoules. Delta H for the last one is minus 163.2 kilojoules. Okay. Now, in the first one, I need to reverse the reaction and I need to divide by 2. So I get NO2 going to NO plus 1/2 an O2. Delta H here is going to be a plus 56.55 kilojoules. Okay, for my second reaction, well, I'm gonna play with my third reaction next. I need 1 N2O. So I've got to take that one and just divide it by 2. So N2O going to 2 N2 plus, let's see, 1 N2 plus 1/2 an O2 is going to have a delta H of 163.3 divided by 163.2 divided by 2. So minus 81.6 kilojoules. Okay, right now I have the correct number of nitrogen dioxides and the correct number of dinitrogen monoxides on the reactant side. Okay? Just so that you know what we're doing. All right. So right now I have 1 nitrogen monoxide on my product side. This reaction has 2 nitrogen monoxides in it, and I've already got 1 there, so really I just need to take that over as is. So I'm going to use this N2 plus O2 going to 2 NO. Delta H is 182.6 kilojoules. Now, if I set this up correctly, when I add things together, I should get my overall reaction. So, let's see. I have an N2O plus an NO2 plus N2 plus O2 on the reactant side, going to NO, 3 NOs plus a half an O2 plus an N2 plus a half an O2, so I've got one full O2 here. So let's look for things that are common. So I have an N2 here on the reactant side and an N2 on the product side. They're going to cancel out. Okay? I have an O2 on the reactant side and O2 on the product side. They'll cancel out. So I've got left N2O plus NO2 going to 3 NOs. Now guys, let's take a close look, okay? Because I know you're at a distance. So let's set this right here so you guys can see, okay, how things cancel out. So that means if all of those added up to give me my overall reaction to get the delta H, all I have to do is add up those delta H's to get my final value. So 56.55 plus 182.6 minus 81.6, and my fingers didn't tap right, 55.6, 56 point plus 182.6 minus 81.6. So I get a delta H for this reaction equal to 157.55 kilojoules. Okay? And guys, good lesson here. If you run into a problem where you get somewhere and it doesn't look right, erase and start over. I do it, you should do it. Okay, you should have the same fortitude as me, or the same willingness to say, oops, I need to do that again. Okay, now, our next kind of twist on Hess's law is that it can be taken a step further. And we can use it in conjunction with standard heats of formation to open up a new and easy way to find the heat of reaction for any reaction. Standard heats of formation, delta H0 formation, is the energy change when 1 mole of a substance is formed from its elemental components in their standard state for the temperature given. The tables at the back of our book are all at 25 degrees C. So when we say standard state, we're referring to a specific set of conditions. For gases, the partial pressure is 1 atmosphere, and the gas behaves ideally. If it's an aqueous solution, the concentration is 1 molar. If it's a pure substance, it needs to be in its standard state under those conditions of temperature and 1 atmosphere in pressure, and it needs to be the most stable form. Most compounds have a negative delta H of formation. Energy is released when we make compounds from pure elements, okay? For an element in its standard state, its heat of formation is 0. If it's in an unusual state, like instead of carbon, standard state is graphite. If you have carbon diamonds, it has a delta H of formation that's not 0. In general, using Hess's law, we can say that the heat of the standard heat of reaction for reaction is the sum of the heat of reaction to the products minus the sum of heat of heat of formation to the reactants. M and N are the coefficients in the balanced chemical equation. Okay? So this really opens up how we can predict the heat of reaction without having to do the experiment. All we need is a table of standard heats of formation and the balanced chemical equation. So we're going to look at problem 9.12, okay, as kind of our last example in the chapter. And problem 9.12 is on page 396. 26. Let's go down, go this way. I'll eventually get in there, guys. Okay. Thermite is a very powerful reaction. Thermite is a very old reaction. It used to be used, and it is still today used, to actually weld together railroad rails. It's a reaction of aluminum plus iron 3 oxide to give us aluminum oxide and iron. And that molten iron is very, 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 very hot. This is a very exothermic reaction. Okay? So it wants us to calculate the standard, using standard enthalpies of formation, the delta H for this reaction. So let me write the reaction out again. 2 aluminum solids plus Fe2O3 solid going to Al2O3 solid plus iron, and that's usually a liquid. Do they have, no, they have it solid. Okay, going all the way to solid. So there's our reaction. Now, what we need to do is look up the delta H's for all of the different substances. Now, embedded in chapter 9 on page 394, you'll find the standard heat of, a very small standard heat of formation table. So I'm going to write in the values. Aluminum is a pure substance. It's 0. Iron is a pure substance. It's 0. Iron 3 oxide, let's see, iron, chlorine, oxygen, silver, come on, give me iron 3 oxide here. Of course it doesn't give it to me. I want it, it's not there. I'm going to have to flip to the back of the book. We're going to look in the appendix. Okay, don't be afraid to use the appendix. You're going to be using it a lot in this chapter. Appendix A has our standard heat of formation table. So I'm going to look up iron 3 oxide. Iron 3 oxide has a standard heat of formation of minus 824.2 kilojoules per mole. For aluminum oxide, okay, looking that up in our appendices, it's minus 1,675.7 kilojoules per mole. Okay, delta H 0 for the reaction is always the sum of the delta H0 formation for the products times their coefficient in the balanced chemical equation minus the standard heats of formation for the reactants times their coefficient in the balanced chemical equation. So I'm going to have 1 times a minus, well, 1 mole times a minus 1,675.7 kilojoules per mole plus 1 mole times 0, and I'm going to subtract from that 2 times 0 plus 1 mole times a minus 824.2 kilojoules per mole. So if we do the math, 1675.7 negative plus 824.2, I get a value of minus 851.5 kilojoules. Notice that the moles and moles divide out here. I'm left in units of kilojoules. Okay, so this reaction, aluminum, 2 aluminums plus 2 moles of aluminum plus 1 mole of iron 3 oxide going to 1 mole of aluminum, and it should be 2 moles of iron has a delta H of 0 formation of minus 851.5 kilojoules. It's an exothermic process. It is a very exothermic process. Okay, guys. And that winds up the chapter 9 part. Go ahead and hit the button. Okay? And what we'll be starting now is chapter 18. Okay? In chapter 9, we were concentrating in on the first law of thermodynamics. Here in chapter 18, we're still looking at energy, but we're going to move on from the first law of thermodynamics and start looking at spontaneity of a reaction based on energy and how they relate. So just to remind you, the first law of thermodynamics, remember, says energy cannot be created or destroyed. So that delta E of the universe is 0, and so energy lost by a system has to be gained by the surroundings. And if we have a system in isolation, the change in energy of that system is going to be 0. Okay? So the first law of thermodynamics helps us track the movement of energy in and out of the system or between things inside an isolated system. But one of the questions they asked was, could the change in energy of the system help us determine whether a reaction was spontaneous or not? Now remember, spontaneous means it happens on its own. Has nothing to do with how fast something happens, just that it happens on its own. So spontaneous change, whether it's chemical or physical, is one that happens by itself under a specific set of conditions. If I set an ice cube out in the room, we know that it would spontaneously melt. But if I put that ice cube in my freezer, we know it wouldn't melt. Okay? So, something that is non-spontaneous but can be something that's non-spontaneous must be continuously supplied energy from its surroundings to keep it happening. So it's got to be fed. Okay? At a glance, first pass, it kind of looked like the first law of thermodynamics was all we needed to figure out if a reaction was spontaneous or not. But when they looked a little closer, things got a little bit more complicated. Okay? Might seem obvious to us that spontaneous reactions need to be exothermic. Okay? It holds true if we look at iron plus oxygen going to rust. Delta H there is a minus 826 kilojoules, and it's spontaneous. And methane plus oxygen going to carbon dioxide and water, it's spontaneous. Delta H is negative. Okay? But at 25 degrees, sodium chloride in the presence of water dissolves to give us sodium ions and chloride ions. It's a spontaneous process. Try it at home. You got table salt in your cabinet. Delta H for that is 3.9 kilojoules, and it's positive. So it's an endothermic process, and it's spontaneous. Same thing for melting an ice cube. At 40 degrees C, an ice cube melts spontaneously, and it's an endothermic process. But minus 40 degrees C, it doesn't. So there's got to be a little bit more than the first law to being able to determine if a process is spontaneous or not. So we ask the question, what's going on? What factor are we missing that took some of those endothermic processes that we would expect to be non-spontaneous and turn them into spontaneous processes? Okay? First thing we have to realize is that enthalpy alone doesn't determine spontaneity of the reaction. There are other factors. Okay? So if we look at the processes that are endothermic but spontaneous, they might help us figure out what's going on. What's driving an endothermic process to be spontaneous? So let's look at a couple of things here and see if we can get a window into what's going on. Dinitrogen pentaoxide decomposes into 2 nitrogen dioxides and half a mole of oxygen and has a delta H of 109.5 kilojoules. It's endothermic and it's spontaneous. Just like I mentioned earlier, sodium chloride solid in the presence of water gives the sodium ions aqueous, chloride ions aqueous. It's spontaneous. Delta H is 3.9 kilojoules. Now, if I look at these two things, I want to know what they have in common that might help explain why it's spontaneous. Figured it out yet? Don't worry, it took a lot of people a long time. If I look at this, notice here I'm starting out with 1 particle and it's a solid, and I end up with 2.5 moles of particles that are in the gas phase. I'm starting out here with 1 mole of particles in the solid, and I'm ending up with 2 moles of particles in the aqueous phase. What we see about these processes is they move from smaller number of particles to larger number of particles, and we move from states where things are very locked down and there's very little movement to states where there's a lot of movement. So all the processes in which systems move from a more ordered arrangement to a process to a less ordered arrangement in process, even though they were endothermic, were spontaneous. So let's talk about freedom of particle motion and dispersal of energy. When a solid melts, the particles go from a very rigid structure where everything is stuck in position, guys, and all the particles can do is they can vibrate a little bit. Okay? I'm here. I can move a little bit. Get out of my way. Bump left, bump right. Oop, I don't have much room to move. They're definitely not social distancing. Okay? So there's not much movement. And as we go from the solid to the liquid phase, the particles can now go, I glide past you. Yes, I got